Welcome to lecture number 16, and in this today lecture we are gonna take from the lecture 15 where we left off, and in this lecture we'll be talking about associativity property, right? Because that's what we were doing in the last lecture. Now we saw example of our first algebraic structure, which was magma, a magma that only satisfies closure property. Then we saw example of a magma, a very different, a special kind of magma called commutative magma, and it satisfied closure and commutativity, right? Now we are going to see a different kind of algebraic structure that satisfies associativity property, right? And we ask, does the set of natural number embedded within binary operation addition satisfy associativity property or not? So in this today lecture we are gonna see that and then see where it goes. Okay, so maybe I should do it on the paper right now. So in the last lecture we saw an algebraic structure which was magma, and a magma, we said, it satisfies a property, an axiom. The axiom is closure property, right? Then we saw a special kind of magma called commutative magma, and this commutative magma satisfied two properties, which is both closure and commutativity, right? Then we ask, so we have here list of axiom. The first axiom was closure. The second axiom was now we are not going to talk about commutative right now. We are going to put it away for a moment, and we want to go to the next axiom called associativity. Now we want to see, does this set, this structure, not set, and set of natural number embedded with an operation, binary operation addition, where we define addition as Cartesian product of natural number to natural number, right? And you want to check if it satisfies associativity or not. So how do we check? Well, we know natural number is set of numbers up to infinity, and it goes on and on. Now, what is associativity? The definition is, associativity says A plus B plus C must be equal to A plus B plus C. If they are equal, then they are associativity. Now we are going to choose three different numbers from this set, right? Because to check associativity or any property, the every element must be from the given set. So for all, this is symbol of for all A, B, C that belongs to this set, then it must satisfy this property, right? For all elements, not only one set of elements, one set of three elements, but it should satisfy for all the set of these three elements that you are going to pick from this set. Now let's choose any three number from this. Randomly we can choose. Let's say A equal to, I'm gonna choose from here 3. Okay, let's say B from here I'm gonna choose, let's say 1, and C from here I'm gonna choose, let's say 20. Now we are gonna substitute this value on this LHS left hand side and this RHS right hand side. So first LHS is what? LHS is this one, A plus B plus C. Now substitute value of A is 3, so 3 plus, B is 1 plus, C is 20. Now we evaluate it. How do you evaluate? First we have to evaluate this expression under the bracket. So 3 plus 20 plus 1 is 21, and now we add this and we get 24. So this is our LHS value, 24. Now for this RHS, so what is our RHS? RHS is A plus B plus C. Okay, now we are going to substitute the same value again. A is our 3, B is our 1, and C is our 20. Now we evaluate first this bracket expression, because we did this here too. So 3 plus 1 is 4, and this is 20, the answer is 20 plus 4, 24. So we saw this value and this value are equal. So this RHS and LHS are equal. It means this and this are equal. So it means LHS is equal to RHS. It means it satisfies closure property, right? Now we can so what happens when a set, now the question, now before the question I want to show one thing, that does this algebraic structure satisfies closure property? Well, yes. What is closure? We know closure property says any element that we choose from this set, for all any two element, for all two element that we are going to choose from this element, it satisfies closure, that is A plus B belongs to this set and this also belongs to this set. So it satisfies closure property and it satisfies associativity too. So what happens? When an algebraic structure satisfies only closure, it is called magma. But when it satisfies both closure plus associativity, it has a name called semi-group. Semi-group. So what we got? We have now this. Let's say we have a table here. This is the name of algebraic structure. These are axiom. Okay. So if it satisfies closure, only closure, then it is called magma. If let's say closure is notation of closure is CL. Okay. Now for associativity, my notation will be AS. Now if an algebraic structure satisfies associativity plus closure, this both, then the name of algebraic structure will be semi-group. Okay. So we have two different kind of algebraic structure we saw. Now we are going to see a different algebraic structure, and that comes from the third axiom. Now what is the third axiom? So we saw our axioms, the list of axioms here. The first axiom was closure. The second axiom was associativity, right? The closure gave magma and closure plus associativity, it gave a semi-group. Now the third property is called identity. Now what is this? Well, let's see. Identity says take any number, for example 5. Okay. Now take a binary operation, let's say addition. So 5 plus, now where is x equal to 5. So identity property says if operation is addition, what should be the value of x such that when you add with 5 you get 5. There is no change in this element. So the answer is x must be 0. It means 0 is the identity element. Okay, because it's not going to change this number, right? So suppose another example could be, let's say we have an element 2. Okay, now our binary operation is multiplication, and here is x. So what should be the value of x? After multiplying with 2 we get 2. Well, the answer is x must be 1 by 2, because 2 into 1 by well, I think I made a mistake here. Okay, so the mistake is not 1 by 2, it is a mistake. Identity element means, suppose we have a number here and here multiplication and x. For multiplication the identity is always 1. Okay, identity is 1. So now What should be the value of x when it is multiplied with 2 we get 1? Well, the answer is 1 by, oh, maybe I'm mixing two things. I'm sorry for that. This is about inverse. We are not talking about inverse. This is inverse. We are talking about identity. So what will be the identity? 2 into x equal to 2. So what should be the value of x? We get 2. Well, the value of x must be here 1, right? If we substitute 1 in the place of x, we get 2 into 1, 2. So 1 is identity element with respect to binary operation multiplication. But here 0 is the identity element with respect to binary operation addition. This was mistake. This was, I was talking about a different axioms. Okay, so don't worry about that. Okay, so we got identity. For example, another identity. What is the identity of 3? Well, what is 3 into x is 3? Well, x must be 1. So we have to remember that with respect to multiplication, the identity is always 1. With respect to addition, the identity is always 0. Now, take an algebraic structure, natural number with addition, where this addition is defined as n cross n to n. Now, does this algebraic structure have identity element? Well, we have to check. Now, for example, we have a notation for identity element. We have a different notation for identity element. It is represented by this letter E. So what does identity means? Well, take any number from this set, natural number. Let's say the natural number is A. Okay, it could be anything, any number from the set of natural number. Now here is our identity element. If we add E with this number A, we should get A. It should not change anything. What should be a value of E? Well, E should be 0. Now question, does E equal to 0 belongs to the set of natural number? Well, natural number has no 0 element. It has no 0. It means this set, natural number with addition, this structure does not satisfy identity property because this set has no 0 element. Well, you can see here natural number start with 1, and since it has no 0, it means it has no identity element. It fails to satisfy identity property. Can we have any set that, can we have an algebraic structure that satisfied identity? Well, there is. For example, whole number start with 0, 1, 2, 3 and so on. Now, does it have identity? Well, we can check it. What is identity? For all A that belongs to this whole number, it means any A that we are going to choose from this A, this is a symbol of there exists an element E called identity within this whole number, such that A, and our operation is plus, remember this, so A plus E will be A. Now what should be the value of E? Well, choose A, any number, let's say 0. So 0 plus what is 0? Well, E equal to 0. So does 0 belongs to this set of whole number? Well, of course, yes. Here is 0, it belongs to. Let's choose A equal to 5. So 5 belongs to whole number, so we can choose it. So 5 plus E must be 5. So what should be the value of E? It should be 0. And 0 belongs to whole number? Yes, of course it does. It means whole number, the set of whole number with operation addition satisfies this identity property. It's called identity property. Now I will give another example. Let's say set of natural number with multiplication. How is multiplication defined? It is n cross n to n. Now what happens to identity element? Well, for all a that belongs, that we are going to choose from natural number, there exists an identity element that also belongs to the set of natural number, such that a multiplied with e equal to a. So what should be the value of e? Well, e should be 1. And does 1 belongs to the set of natural number? Well, yes, natural number has 1. It means the natural number with binary operation multiplication has identity element. It satisfies identity property. But natural number with binary operation addition has no identity element because 0 does not belongs to the set, right? So this is called identity property, right? So now what we saw, now we have to classify few things. Here is our axiom. So if first is closure, an algebraic structure if satisfies, it's called algebraic structure. An algebraic structure that satisfies closure is called, we saw, magma. Now second, closure plus associativity. If an algebraic structure satisfies both this property, closure and associativity, it's called semigroup. Now third, if an algebraic structure satisfies closure, associativity and identity property, all three together, it's called monoid. Remember this, it's called monoid, right? Now the example of monoid is natural number with addition, because it satisfies closure property, it satisfies associativity, it satisfies not addition, it should be multiplication, because with multiplication it has identity element. So it satisfies all these three property, natural number with binary operation multiplication. So it is an example of monoid. Okay, it is monoid. So we have seen, so we saw three different kind of algebraic structure: magma, semigroup, monoid. Now the last is there is an axiom. The last axiom is called inverse. Okay, now if an algebraic structure satisfied closure, associativity, identity and the last property inverse, it's called group. Group is more powerful than all these structure. Now what is inverse? Well, let's take a set G, it could be anything, and let's take a binary operation star. It could be plus, minus, subtraction, anything. How this star is defined? Well, star is defined from G cross G to G. Okay, so what is inverse? Inverse is for all element A that we choose from G, there exists an element A inverse. The notation of A inverse is A inverse. It is not A power minus 1, it's just A inverse. The A inverse belongs to this set G. For any element that we choose from this set, there exists an A inverse in this set G, such that what happens? When A is operated with A inverse, we get identity element, and the identity element must also belongs to G. Right? This is what we mean by inverse property. Now we're gonna see this property in action. For example, let's say set of real number. It contains all number -3, -2, -1, -half, 0, and then 1, 1/2 somewhere, 2, and there will be √2. Here will be √2 and so on. All numbers, real number contains. Now does it satisfy inverse property? Well, we will see this in the next lecture. Does real number with respect to, let's say, multiplication has inverse or not? So for now, thank you for the lecture.